How are we doing today? Today we're going to start a unit on moles or stoichiometry. Basically what that means is it's chemistry math or math of chemistry, and ultimately at the end of the unit we're going to be able to write a chemical reaction, and then if we want to make 10 grams of the product, how many grams of each of the reactant we would need, or how many moles of each of the reactant we would need. All right, so that's kind of our end goal. It's going to take us a little bit of time to get there, but here we go. All right. So I want to know what you know. I'm going to ask this question on Edpuzzle to see what you know about this. So what is the chemistry mole and how many atoms are in a mole of carbon? So a chemistry mole is, all a mole is a word that represents a number. All right. You guys are familiar with one word that represents a number is a dozen. All right. If you hear the word dozen and it means 12. All right. I think everybody knows that. And there's lots of words that mean numbers as well. In chemistry, we deal with a very specific number. It's actually a very, very large number. All right, it's a mole, and a mole is equivalent to 6.02 times 10 to the 23rd. I'll show you what that number is in a second. So if you have 1 mole of something, you have 6.02 times 10 to the 23rd of that thing. All right, chemistry is really the only place you're going to get enough of them to have a mole or a half a mole or 7 moles or whatever, because it's the only place it's going to have a small enough particle to do that. And I'm going to give you some what I call ridiculous mole facts in a second to show you how big that number actually is. It's a ridiculously big number. All right. And how many atoms are in a mole of carbon? Just like I said, 6.02 times 10 to the 23rd. Okay. All right. So intro to the mole. So a mole is just a word that represents a number. It's not this little creature up here. It's not a mole that grows on a person's body. All right. So I asked how many are in a dozen. I think everybody knows a dozen is 12. All right. There's something called a baker's dozen. Which is 13. All right. And the reason why the baker's doesn't exist is because when a baker makes something, they want to have an extra to test to make sure it was okay. Okay. How many are in a gross? You may or may not be familiar with the term gross. A gross is an old school term. If you buy lots of stuff, it might say there's 10 gross of them in here. A gross is 12 12s, which is 144. How many's in a ream? You guys are familiar with reams, probably with reams of paper. All right. A ream contains 500 pieces of paper. All right. And how many reams are in 5,000 sheets of paper? All right. So if you divide the 500 into 5,000, you get 10 reams, which is a case of paper. All right. That is kind of where that comes from. A score, really old school thing. A score, they make a tick mark to count. A score represents 20. If you've heard of the term 4 7 years ago, and the Gettysburg Address, so that's 87 years ago. So those are all words that represent numbers. There's multiple. A couple means 2. All right. So there's lots of other ones. Those are just the ones I'd like to talk about. Now we're going to get into ridiculous mole facts. All right. This is to try to show you how big the number 6.02 times 10 to the 23rd is. All right. So 3 moles of M&Ms would fill all the oceans, but 3 moles of water is about a quarter cup. So think about that. Now, generally speaking, we think of M&Ms as being a pretty small thing, all right, but they're enormously large compared to a molecule or an atom. All right, so if 3 moles of M&Ms would fill all the oceans on the earth, 3 moles of water is about a quarter cup, or a decent sized sip. All right. A mole of donut holes. So everybody likes donut holes, I think, anyways. All right. A mole of donut holes would cover the entire Earth 7 miles deep. So you'd have 7 miles of donut holes on top of you if we had a mole of donut holes. So a donut hole is just going that much bigger than an M&M. So that's how big this number is. All right. A mole of pennies stacked like that picture would reach to the moon set between 7 and 8 times. All right, so that's what a mole of pennies would be. And we'll talk later and on the next slide or the slide after about how much money that actually is. All right, a mole of seconds is 19 quadrillion years, all right, which is 4.2 million times the age of the Earth, or almost 1 million times the age of the universe. So if you try to count to a mole 1 second at a time, that's how long it would take you. All right, not going to happen. A liter bottle of water. So one of the bigger bottles of water is 55.5 moles, and the reason being is because the molecule of water is so small. All right. This is the one that's interesting to me. If you started with a mole of pennies and spent $1 million every second for 100 years. At the end of that 100 years, you'd still have 99.9% of the money you started with. That's how crazy big this number is. All right, so it's 602 with 21 zeros after it. It's an enormously large number. The only place you're going to encounter things of this quantity is in chemistry, and that's why it's a new term for us. So and you got to start to learn the terminology and what it means and stuff. Okay, so here we go. All moles created equally? No. So if you look on the picture here, we've got apples and paper clips. All right, I think everybody in here can count that there's 7 apples and 7 paper clips. All right. What if I said, instead of having 7 apples and 7 paper clips, I had 7 pounds of apples and 7 pounds of paper clips? Because sometimes things you measure, you kind of indirectly count them by their mass because it's too tedious to count them individually. So if I had 7 pounds of paper clips and 7 pounds of apples, would I have the same number of apples and paper clips? And I think everybody would understand that no, we would not. All right, we would actually have more paper clips than apples because a paper clip has a much smaller mass than any apple. All right, but we need an equal number of apples and paper clips because, well, let's say we're doing a project where we're sticking a paper clip in an apple and using it as a photo holder or something. All right, so we have to be able to make these conversions between, in this case, pounds to numbers of apples, all right, or pounds to numbers of paper clips. But in chemistry, we don't really deal with pounds. All right, we deal with moles or we deal with grams. So we're gonna have to make these conversions. So this unit becomes lots of math. So how an atom reacts depends on the number of atoms, not the mass of the atoms. All right, and realistically, it has to do with the number of valence electrons. All right, so we don't generally count atoms in chemistry. All right, we're gonna get a mass of them and be able to correlate that to a certain number of that particular atom or particle. All right, is it feasible to count atoms? Look at a mole. So here, I think this will work. I tried to set it up so it would work. Hopefully it does. On here, I'm just going to minimize this down. I have a mole of salt and a mole of sugar. So I have 2 different graduated cylinders here. All right, and you can see that they're significantly different in size. The one in my hand right now is salt. All right, so this is 1 mole of salt. All right, so you can look at it here. It's got approximately that volume. I think you can see that it's smaller than this one. This molecule, this container here, contains a mole of sugar. All right, and you can see that the volume is nowhere near the same, which I think most people would appreciate that the mass is not the same either. All right, but the only thing that's the same between these 2 things is the number of molecules or particles. All right, they both have 1 mole of them. Now I'm going to compare it to just an individual element. All right, so here I'm going to put on the screen, on top of this is a mole of copper. That's how much a mole of copper looks like, or what a mole of copper looks like. All right, this one here is a mole of aluminum. You can see on here it says 1 mole. They're not the same mass. If we were in class, I'd have you pick them up. This one in my hand now is significantly lighter or less massive than the copper one. But what's the same between all of these samples is the number of things that make them up. And I say things intentionally because in the sugar, it's a molecule. In the sodium chloride, which is an ionic substance, it's a particle. In these 2 things, which are pure elements, they're atoms. So things can mean lots of things, if that's such a thing. I just kind of chuckled at that one. All right, so things can mean many different things, so you have to understand what they're referring to. Okay. So now we're going to go back to the notes. If I can get to them, I think I can get to them. Where are they? They're here. Okay. So look at the bullet. So do you count the particles? No. We have a measurement, whether it's by mass or volume, of how much is in a mole. All right. But what could you measure? You can measure the mass. You could do that easily. You could actually measure the volume as well. All right. But we're going to make some correlations between this. I'm not going to leave that bottom part up. All right. So here we go. What's the mass of a carbon atom? So this is where you need your periodic table. So hopefully you have it available to you. I might bounce back and forth between my periodic table and this screen, but probably I'm going to refer to it in a lot of ways. What's the mass of a carbon atom? So here you're going to look on your periodic table. All right, so you're going to look on your periodic table, and you're going to, I'm going to do this because I think it's valuable. So carbon's right here. So this is kind of a symbol of what carbon is right here. It's a little bit bigger. All right, so this number here can mean a couple different things. If you have one carbon atom, this is its mass, 12.011. All right, we will always round our masses on the periodic table to the 10th of a decimal point, so 12.0. It would be the mass of that. One mass of, and I'm going to pick out some challenging ones for people. The mass of chlorine, I think you guys can see this screen. I think it's in focus enough. The mass of one chlorine atom, it says on here is 35.453. If we round that to the 10th, it's 35.5. All right, aluminum, all right, would not be 26.9 because that 9 gets rounded up because we're rounding to the 10th. So we got to look at the next number after the 10th because that's an 8. That becomes a 0. This becomes a 7. So the mass of aluminum would be 27.0. So now when you pull a mass off the periodic table, you have to round it to the 10th and you have to be correct in your rounding when you do so. Okay? So when we go back to our notes, so the mass of a carbon atom is simply put is 12.0, and the units we're going to refer to now is called AMUs. We talked about them earlier in the year. Atomic mass units, which is kind of a made-up unit. We're not going to go into that right now. All right, but what's neat or what works out conveniently for us is that if we change AMUs to grams, that's the mass of 1 mole of carbon atoms. So 1 mole of carbon atoms would have a mass of 12 grams. So if you have 1 mole of carbon atoms, how many atoms would that be? That'd be 6.02 times 10 to the 23rd atoms of carbon. If we had 6 grams of carbon, we would have half that number in atoms, so 3.01 times 10 to the 23rd. If we had 2 moles of carbon, it'd be twice that. Or I could ask you, if you had 12.04 times 10 to the 23rd atoms of carbon, how many grams is that? That would be 2 moles of it, so it'd be 24 grams. Okay, so the masses on the periodic table can be 2 different things. It can refer to the mass of one particular atom, or it can refer to the mass of 1 mole of that stuff's atoms. Okay, so what we're going to use this for is we're going to talk about what's called the GFM, gram formula mass. All right, I have molar mass in parentheses. It's an old school terminology. All right, but I will always refer to this as the GFM. So the GFM is the mass of 1 mole of something. So if I were to look at our this screen right here, and I'm going to bring it over here intentionally. So the GFM of carbon, because carbon's a monatomic element, would be 12. All right, the GFM of neon would be 20.2. The GFM of oxygen would be 32. Why would oxygen be 32 if its mass is on the periodic table of 16? The reason why oxygen's GFM is 32 is because oxygen is diatomic. Remember those diatomic. So if we go back over here to hydrogen, hydrogen's an easy one. Hydrogen's mass of one atom is 1. If you had a molecule of hydrogen, or if they just ask you what's the GFM of hydrogen, you would have to use 2 because hydrogen is diatomic. You need 2 of them. Okay, so the mass of 1 mole of something is the GFM. So let's try out water. So now what we're going to do is we're going to do the GFM of a compound. Now we start off easy and then we get harder. This is the simple basic thing that you need to be able to do in here. And I'm going to you're going to want to pause the video to do these. I'm just going to kind of continually talk so that the video is not as long as it could be. All right, so we're going to try out water. So to be able to figure out the GFM of a compound, you need the formula. I think everybody knows the formula of the water is H2O. All right, so now what you're going to do is you're going to list the elements in your compound. So in this case, we have 2 elements, and I'm going to recommend that you do it the way that I'm doing this, specifically this way. It's going to make life easier later on in the unit. So in this compound, we have hydrogen, we have oxygen. All right, now we have to identify how many atoms of each of the elements we have. So here we have to take into account subscripts. These are the subscripts. All right, so since there's a 2 next to the hydrogen, that means we have 2 hydrogen atoms. And then there's no subscript here, which means it's a 1, so we have 1 oxygen atom. So now to figure out the GFM for water, what we have to do is we have to look up the mass of hydrogen on the periodic table. We have to look up the mass of oxygen on the periodic table. Hydrogen's mass, rounded to the 10th, is 1.0. All right, and notice I put this times this, and we'll talk about that in a second. Oxygen's mass on the periodic table is 16.0. To get the GFM of water, we have to perform this math. So we got 2 times 1, which I think everybody can do, is 2. And 1 times 16 is 16. To get the GFM of water, now we add this up. It's 18 grams per mole. I will tell you, the most common mistake by kids is to add up this column right here. They don't distribute the math for the number of atoms. They just add up the elements. All right, because water has 2 hydrogens in it, you have to account for that. And you have to have the mass of 2. So the GFM for water, so if I asked you to go get me 1 mole of water, you'd have to give me 18 grams. If I asked you for a half a mole of water, you'd have to give me 9 grams. Okay? All right, so that's GFM, and that's literally all we're going to do the rest of the day and for the beginning day. So therefore, water has 1 mole, or a GFM of 18 grams per mole. All right, so now we're going to do another compound, magnesium hydroxide. So this is where I'm going to stop, and I'm going to ask you what is this formula for magnesium hydroxide, because they do it in class. All right, you have to crisscross jump jump. When you crisscross jump jump, and hydroxide is not H, hydroxide is a polyatomic. When you crisscross jump jump, you get MgOH2 for the formula of your compound. All right, to get the GFM, we write down the element we have. So in this case, we got magnesium, we got oxygen, we got hydrogen. All right, magnesium has 1 atom in here. All right, because there's a subscript there of 1. Now, because of the parentheses, this 2 is going to distribute to both the oxygen and the hydrogen. So in this case here, there are 2 oxygen atoms and there are 2 hydrogen atoms. Now, once I get the number of atoms in the compound, now I have to go to the periodic table and get their masses. So now you go to the periodic table, get the mass of magnesium. Magnesium is 24.3, rounded properly. Oxygen, if you can remember from before, or hopefully you'll remember pretty quickly, is 16.0. And then hydrogen is 1.0. Do not add up this column because we did not account for the number of oxygens and hydrogens. So we had to do the math across first. So 24.3 times 1 is 24.3. 2 times 16 is 32. 2 times 1 is 2. Now to get the GFM of magnesium hydroxide, all we do is we add these up. All right, and you get 58.3 grams per mole. All right, so if I told you to go measure out 1 mole of magnesium hydroxide, that's what we would do. Okay? All right, now we're going to do sodium nitrate. Once again, it's another compound I'm going to ask on Edpuzzle, what is the name of the formula for this? So you look it up. Sodium nitrate's formula is NaNO3. And this is something you need to be able to do pretty quickly at this point in time. Whether you put parentheses in it or not doesn't matter at this point in time because the subscript's a 1, so it doesn't matter. I'm going to put the parentheses there. Try to remember to do it so that it reminds you to do it as well. All right, so GFM. So we've got to write down the elements we have. In this case, we have sodium, we have nitrogen, we have oxygen. All right, the number of atoms. Sodium is number 1, or it has 1 atom. Nitrogen has no number outside the parentheses, has no number here, so it's a 1. And then there's no number outside, so it's a 1 times 3 for oxygen, so we have 3 oxygen atoms. Now I have to look up the GFMs for sodium, nitrogen, oxygen on the periodic table. This is where you're going to want your periodic table there with you all the time. All right, sodium, when you look up, has it rounded correctly is 23.0. Nitrogen, when you look it up, rounded correctly is 14.0. And oxygen, hopefully you know by now, oxygen is 16.0. All right, so now do not add this column up because we haven't taken care of for how many atoms we have. So 1 times 23 is 23, 1 times 14 is 14, 3 times 16 is 48, and now we add them up. All right, and when you add them up, you get 85 grams per mole. So you can see that the GFM of 1 mole of sodium nitrate is 85 grams, which is a little bit bigger than the previous compound, which I can't remember, it was magnesium something. All right, okay. So that's all we're doing right now. So now I'm going to show you another type of compound that can be written. It's called a hydrate. All a hydrate is, it's a compound in which ions are attached to 1 or more water molecules, but it's written differently, and that's why I want to show it to you. So sodium carbonate, a hydrate is written like this. You got sodium, you got the carbonate, and then you have a dot. It's a big dot, and it's times water. Now this is technically sodium carbonate decahydrate because there's 10 water molecules. There's another sodium carbonate that would be pentahydrate, which means this would be 5. All right, but all we're concerned with at this point in time is being able to do the GFM. So just like the other compounds, we write down the elements we have. So in this case, we've got sodium, we've got carbon, we've got oxygen. When you get to hydrate compounds, I'm going to recommend that you keep the water as H2O. Don't split it out to hydrogen and oxygen. So you're going to leave water as water. So now all we do, now that we have everything listed, now we go back and identify how many atoms or particles of each we have. So here for sodium, because it's got a subscript 2 there, we have 2 of them. Carbon has a 1, and that it's got no subscript, so that's a 1. Oxygen has a subscript with 3, so there's 3 of them. And water, there's no subscript after water, but there is this thing here which is called the coefficient, and this tells me that I have 10 particles of water, so that's going to be 10 of those. Okay, so now we go to the periodic table, and we get the GFM of sodium, which is 23.0. Carbon is 12.0. Oxygen we look up is 16.0. And now water, and water is a very simple compound, and we did it already. If you look back in your notes, you can get the GFM of water, but water's GFM is 2 hydrogens and 1 oxygen, which is 18. Okay, so now we got 2 times 23 is 46. 1 times 12 is 12. 3 times 16 is 48, and 10 times 18 is 180. Now you just add all these up, and when you add all those up, you get 286 grams per mole. So it's a pretty massive particle for sodium carbonate decahydrate. Okay, so now what I'm going to do is, we've seen enough of these practice-wise. All right, so now what I'm going to do is I'm going to put up some problems. I think I can put them all up. Yeah, there's 10 of them on here. I recommend, if I were you, I would do, evens or odds, whichever one, so you can get practice with it. And in a minute, I'm going to give you the answers. But first things first is I'm going to ask you for the answer for this one right here. I guarantee on Edpuzzle. So sodium bromides, when you do this, that's the mass for sodium bromide. You got lead sulfide's answer is there. So you have all the answers here, and I'm not going to let the video run. You can just pause it and do these. All right, but I will ask different questions on Edpuzzle. And that's it for today. There's a couple of songs out there that are kind of funny. I'll put those links on Google Classroom for you.